Just sit on your seats.
OK， 我们中间呢有点空，左右两边的可不可以往一下大家？各位左右两边的老师同学，稍微往中间移一点点好不好？这样显得中间饱满一点。好，谢谢各位啊。
That open the session. So let's enjoy the rest of the conference and look forward to seeing many stimulation discussions and fruitful collaborations take place over the next few days. Please, Sheffield.
Yeah, thank you very much. You have heard my name already. So I'm from Berlin, Germany. This
Thank you very much, Matthias, for this kind of introduction. And also, I'm very happy to be here to share with you some of the results. So also many thanks to the invitation from me. So I'll be talking on okay. So the AI-powered DFT methods. And so for this years, we get very familiar of this picture, and so we all agree that there's a paradigm change of the science from empiric science to this model-based science and to computational science and to the big data-driven. To big data-driven science, and of course, so as you can see here, I changed the title a little bit. Unlocking the future of material science with AI. So we actually know that with accumulation of the data from experiments and also from simulation, and now we can use machine learning algorithm and to dig out the unseen principles from data. So the acquisition of data is really important. And of course, we see for many years the quantum power of computational materials. In fact, computational materials has already developed itself into an important and independent field of study within natural science. And so there's no need for experiment synthesis and characterization a priori. And what we need is only the structures, the composition, and then we can do the first principles data. And nowadays, with machine learning, we also see the data powers. And so with all this data accumulate, and we can have an integrated approach that combines experiment data and computational data and machine learning. And so we can form a closed loop to accelerate the development of materials. But of course, we also face challenges, and this is a cover from Nature many years ago. You can see this is 2016, and so this is for the materials code, and we see that machine learning techniques could revolutionize how materials science is done. And the positive message is we are now seeing a real convergence of what experiments want and what the series can deliver. But there's also the other headline saying that truth is some of our errors comes with series, and we may never be able to correct them. So this is a more recent editorial also published on Nature, and saying that for paves, the AI revolution has yet to happen. So it's only until we can get accurate and accessible training data, and we can achieve the full potential of this data-driven science. Otherwise, it would be just a hype over a hope. So this is actually the main theme of today's talk, and we're going to talk the development of a new density functional that can be more accurate, to give more accurate results. Because in practice, we can only use approximate functionals, so errors are unavoidable. And can we develop efficient yet accurate ways to correct errors from the existing DFAs, so all the data accumulated in the literature can be reused. And with this accurate data, maybe we can develop some surrogate models that can speed up the materials development. So, of course, DFT is an exact theory, but the D1 functional is unknown. So approximations are needed and quest continues. And so over the years, there are many functionals have been developed, and this is produced view to group all these functionals into the 5 lines. And today I'll be emphasizing the top line because this is we have the best chance to approaching the chemical accuracy. And also, we have developed the XYG3 double hybrid functional, which not only includes the hydrophobic parts as the exchange, but also the perturbation as the initial slope of this adiabatic connection formalism. And this is Igor, and he used to work with Matthias Scheffler in Berlin. So, of course, with the increase, inclusion of this perturbation, and we have to care about the accuracy and the efficiency. And we know that it's only when 2 electrons, they are opposite spin, and in close proximity, they can make a chemical bond. And so we may only do the opposite spin calculation with this perturbation term and leave the same spin part be treated by the DFT. In this way, well, we can gain efficiency and accuracy at the same time. So this is a calibration on heats of reactions and reaction barrier heights and non-bonding interaction, and also potential energy surface. And in this way, we can actually get improved. We can get energy data with improved accuracy. But of course, in addition to the energy data, we also need the property data. And so for this years, we have been developing the analytic gradients for the XDH functionals. And so this is a calibration on vibrational frequency and NMR chemical shading, for example. So you can see with this XYG3 functional, we can actually vibration frequency prediction, and MAD is around 10 wave number. And also we can push the MR chemical shading to 1 ppm for the carbon 13. But of course, AI machine learning can also help to develop advanced DFT functional, and this is one of the well-known examples with a DeepMind group. And we also have this deep learning XDH, and so starting from this BAK88 and YP as exchange and correlation respectively, and we can use machine learning to construct the scaling factors. And so in this way, we can in hope to improve the accuracy. And this is the results, and also using this GMTK and 55 sets, which includes many single point calculations and energy, relative energy data for chemistry. And you can see that this is the DM24, and this is our original XYG3 and also XYG7. And with this machine learning data, and we can reduce this mean absolute deviation dramatically. And also, it's very important that we can remove the self-interaction errors dramatically at the same time. And this is with SMB and also a PhD. He was a PhD student with Matthias Scheffler. And so we believe that AI can help a lot when you are seeking there are many different factors that can make this contribution. For example, for one-to-one interaction, maybe plus D dispersion plus D is quite okay. You have really simple expressions because the physics is really clear. Yeah, you have the R6, R8, R10 dependence. But for this strongly correlated system, there are many different factors which can contribute to this, and the definition is sometimes very ambiguous. And so machine learning actually can help a lot in this way. And so we construct a small data set for bound breaking, but you can see that the gold method of quantum chemistry, CCSDT, will fail badly for this kind of chemistry. But with this machine learning, we can actually get a very good discussion, the dissociation curve for all this. And so you can see this is not with sacrifice of the main group chemistry. At the same time, you can get good performance for the main group chemistry and also this strongly correlated system. And this paper just appeared in Jack's Gold. And with this, we can do this dissociation on the surface, and this is one example for the methanol dissociation on the surface. And we compare the results with PBE plus D, and this is very commonly used in the literature. And you can see that the dissociation curve is very different from PBE1 and this new machine learning functional. So of course, as we already said, that in practice we use functional, which is low level. For example, for PBE for materials and also BSRIP for chemistry. And so we have already accumulated many data. Can we have a way to remove all these errors? This is an early day paper by Schreier and showing that there's a huge error for the heat formation, and with the increase of the chain of the N-alkene, and you can see B3 errors as compared to the G3 level, which is a couple class plus D. And you can see the errors is increasing, and as the chain is getting increased. And this is not the specifically for BSRIP. And in fact, all the functional at that time has this similar errors. And so, but when you look at the literature at that time, BSRIP is actually the #1 choice, and people, more than 80% calculations are done with BSRIP. And this is a conclusion from Schreier's paper, discourage the use of BSRIP models for reaction energy calculation of organic compounds containing more than 4 carbon atoms. So in fact, we use DFT because it's efficient. But then, with the system is getting large and the error is getting large. So at that time, we've been thinking that maybe we can use neural network to correct the BSRIP results and to get improved results. And so we've been working along this line, and I can show you some examples. So it's not for heat formation or atomization energy, you will argue that you breaking every bond of this molecule. Sometimes I'm only interested of breaking one bond. So you can see so you can see that Okay, you can see that B3 lip adults is actually getting increased as the branch of massive substituted alkenes is progressive increased, and you can see the adults is increased. And so this is our original machine learning with artificial neural network, and this is including the spin correction, and this is also consider the environmental effect, and you can see the bonding dissociation entropy is getting improved. And also at that time, we noticed that, so it's very important for the data representability. So if this is for CH molecules are concerned, and so all this basic species has captured fundamental properties of the. So if only you include, if the data set is small, you only include this 55 selective CH molecules for the training set, into the training set. If you increase this to say 100, and maybe you distort the data represent of your chemical space. And of course, if this is nowadays this is deep learning, you have as many data as you want, and then this is another way. So if you can only have a small set of data, and the data representability is really important. Also, the selection of the descriptor is also very important. Already at that time, we noticed that maybe you should use this 3D and coding the atomic information into the nodes, and also the chemical information into the bonds. And so, of course, this is very simple 3D models, but the performance is quite good. So, as we already shown that with for the heat formation of an N-alkene, and you can see X3D is really satisfactory, and even comparable to the G4 theory. And of course, for G4 theory, it's really difficult to get molecules in this size already. And this is for polycyclic saturated hydrocarbons. And so only this one is included in the training set, but we are able to get very good performance for this set of molecules, and you can see B-slip for this set is already around 30 kilocalories per mole, and again this is comparable to the G4 theory. So we have examined different properties of the CH, and you can see that this is original B-slip adults, and with this machine learning correction, you can get much improved results as compared to the CCSDT results. So originally, this was submitted to JCTC, and at that time, it's very difficult to get the paper published, and roughly is confused and saying that DFT is the first principle. Why you should amend this empirical methods? So now I believe everything has been changed. And of course, state of art. The one of the cornerstone is nowadays the GNA for so I take Shinad as an example. Alexander is here, and you can see with this training. You can get very good results for this optimization energy, which is 14 milli-electron volt. But what we're saying is that the chemistry is really complicated. So here we show you different isomers of this same composition, and then at this time with the prediction, and now the error is huge. And so this means so for doing chemistry, you need to be very careful, and also the chemistry data are very self-consistent. You can construct as many as this isomerization and as a check to see how good the data is. And so now we can extend the X1 to X2 and also using the same work. And of course the label data is at XDH level, and we can do BLYP, a small DFT calculation in the first place, and then we can do this this data learning at the beginning for the X1. We already collect XYG3 B-slip to the G4 results, and this is this share the same split today's data learning, and so you can see that with this this prediction for this S2, and you can get very good results for this isomerization. So also I have 5 minutes left, and so with all this good data at hand, maybe we can thinking about developing the surrogate models that can speed up the materials development. And of course, there are two main directions. One is machine learning for force fields, and the other is to predicting molecular properties. And we believe that the GNN, of course, is one of the direction, and also with GNN and using this equivalent property, it's very important because this is the intrinsic the fundamental properties of a molecule, so the NN system has to obey. And this is a summary from literature showing that the progress in predicting molecular properties was the GNN. And so here you can see that the pi-NN is one of the state-of-art models. And so we extend this X-pi-N to pi-N to this X-pi-N, and this is what we have been done. We have been modified the embedding instead of using this one-hot encoding, and we use space set projection, and also we use okay, maybe so. Here's for the atomic layers, and this is for the message passing. And for the message passing, we include this radio-based function, and also this real spheric harmonics, and so we can expand the relative position and introducing positional information into the message, the message passing. And this is for node updating, and we also have some modification here. And we're also training two models. One is direct, and the other is based on XTB. And you can see that the results are X-pi-N as compared pi-N, it's always win over the pi-N results. And if you include this XTP as a baseline, and actually you can get much more improved results. And this is not only for energy, but also for force. And you can see the X-pi-N results and X-pi-N results as at XTB. And not only properties, you can also do the potential energy search, and this for the geometry optimization. So we can really use this model to do some applications when DFT is very difficult because of it's very time consuming, and also it's not accurate enough. And this is one of the reaction, and you can see this is experimental results, and this is our best prediction, and this is omega B 97M plus D, and this is already state-of-the-art DFT calculations. And you can see that this is where, at this space set, this is very expensive, so it's unaffordable for this reaction. And of course, semi-empirical methods alone is not good enough to get good results. And this is a comparison on the computation time. And also, we have proposed the first general purpose module for which can predict tensor property of arbitrary rank and intrinsic symmetries. And so we as compare the most recent other existing machine learning data, we can have very good performance on this. And this is the good performance remains for the symmetry of any crystals, and meaning that we have achieved ideal learning for the complete fourth order tensors. And so with this, we can actually do materials prediction, and we use this to do material screening for the potential super hard compounds. And in fact, we have identified 13 compounds which are not in the data set. So I would say that the central role of density functional theory in the AI age, this is what I agree with, is the data generation. But I will also quote Matthias Schäfer's saying many years ago that the electronics structure theory is a base for multi-scale modeling of materials property and function. Obviously, if the need accuracy is lacking at this space, there's little hope so that the accurate prediction can be made at any level of modeling as follows. So nowadays, we may emphasize more on efficiency, but we believe that the accuracy is very important. You need to be accurate enough, and so you can do good simulations. And so, of course, for DFT, we need to work on 2 legs. On one hand, we should develop the more and more accurate functionals. And on the other hand, we should develop the efficient yet accurate ways to correct the errors from existing DFAs with this, and then we can develop the surrogate models that can speed up the materials. So many thanks to the team members and collaborations, and with that, I would like to thank you very much for your attention.
Question to you. Is there a way that the advanced chain correlation function that you apply for some system which has not been studied so far? How can you actually judge the reliability?
Oh yeah. So because things are none, so you cannot judge it, right? But the confidence comes from the calibration on the none system. Mm-hmm. So for the none system, of course, you can also separate this from training and validation. And in fact, for DFT development, we are not rely so much on this training. Mm-hmm. We need everything is physically motivated, and so we can have the reliability of the future prediction. And also, we believe that at this at this age of AI age, and of course we already have this surrogate models to speed up, but then it's very important to form this closed loop, and when you have this this final prediction, and you can do the DFT and the experiment validation and posterior. Yeah.
Okay, thank you. I think there was one question somewhere there. I don't see that any. Okay, yes, you were. Okay.
Thank you very much for this nice talk. I'm Jackie from University of Louvain in Belgium. So my question is, you were talking about the molecular a lot. How about the inorganic materials? How about if we apply the new exchange correlation functionals to the inorganic materials?
So yeah, thank you. So you can see that we're using this G1, G2, and G3 set. This is only one example, and this includes organic molecules and also inorganic molecules. And also we have been applying this to the transition matter catalysis. And so in fact, in our data set, we have included all the inorganic and organic. And as so for this GM-TKN55, this includes, as you can see, the barrier heights and basic properties and interaction, non-covalent interaction. And so this actually includes inorganic and organic reactions for, yeah.
And crystals, do you have any results?
Yeah. So for this, so you can see this is the performance of this machine learning. So this is the DM25, and so this is actually the independent test. We never fit using this GM-TKN55. We never do this fitting against this base set. All of these results are totally independent testing results.
Thank you very much.
Okay, I think I've seen two more hands, but we are running 10 minutes late already, which of course is taking away from your lunch break. So I think actually, please excuse me that we don't take more questions. Thank you very much again to Qingqu.
Thank you.
So we continue, and we now have two invited speakers. These invited talks are 17 minutes long. And again, I will make a signal. That means actually, if you see my hand, that means there's 5 minutes more to go, so that we have a little time for discussions. Our next speaker is Lifeng Zhang on AI-empowered materials design, transforming collaboration paradigms and overcoming incentive barriers. Oh, should I keep this?
Okay, thank you, Matthias, for the introduction. And hello, everyone. I'm Ling Feng, and I would like to thank, in particular, Professor Liu Yi for the organization and all these organizers and pioneers in the field, in the committee session. And I'm very honored to share some thoughts, maybe in a different way. I think to those trying to integrate AI with scientific problem at a very early stage, I think yesterday could be a very sleepless night. So so actually these days, what makes things particularly challenging is that I do feel that there could be several very exciting opportunities, but what we really need to revisit is the way we organize the efforts. In the sense that, for example, we all know like ChatGPT and transformers and all these kind of advances in the field of AI, but what led to such a quick development of so many technologies? I think it could be like frameworks like TensorFlow, PyTorch, and communities like Hugging Face, and also special kind of organizations like DeepMind and OpenAI. So that's what the field in typical scientific research is lacking. And a typical scientific community is driven by peer-reviewed publication system, and typical, very typical. And what could be different? That's the starting point of my talk. And also in so I think that's title, transforming collaboration paradigms and overcoming incentive barriers. I do feel there are so many unnecessary incentive barriers that are truly blocking things. Okay, so then at first I would like to introduce maybe how I came into this field. So I went to Princeton with a background of physics and math. So I went to apply math. So I think the very first thing I learned with my two advisors, Professor Wei Nan Yi in applied math and also Roberto Carr in computational chemistry, was like multi-scale modeling and learning of the microscopic world. So this is a pioneering work, Carl Parnell, MD, and I think every year of yesterday, we may expect that this could be like honored by this Nobel Prize award or not. So, but unfortunately this year, no. And but it's truly the pioneering work that integrated the two communities, electronic structure and also molecular modeling. And then we know that the learning story happened pretty early. I think it could be dated back to early like 1990s. But as far as I know, we know like nearly 20 years ago, there have been like work like parallel neural networks, integrating neural network architectures with the potential energy surface, and that's even like 5 years ahead of like the AlexNet breakthrough in machine learning in 2012. And also what was interesting and what the first story Professor Wei Nan Yi told me when I went to Princeton was that he thought maybe there's not much left for multi-scale modeling because there have been so many methods and schemes developed, and there are essential bottlenecks, which could be something that we don't have good numerical schemes in applied math. So I will explain later. But then he claimed that in the year 2011 that he wrote this book, Principle of Multi-Scale Modeling, and he claimed that he will turn to big data and then machine learning, then AI. So that was the year of 2011. And then actually I would say like the year of 2016, when I went to Princeton, those are the stories before all this field. And then actually the very first meeting Wei Nan collected with Roberto and me was to ask the question, so what would AI bring to molecular modeling? That was the very first meeting of my PhD period. So we had a very thorough discussion, and I think Roberto was quite critical in this opportunity. And so he told us a lot of potential challenges. And what was interesting was that after that discussion, I started to do some literature review and started to learn what neural network is and what we could do from that. And then I sent this email to Wei Nan. So my major point is that this has been solved like 10 years ago by this paper by Michele Parnello and Jock Beller, because that was already like 10 years work. And we all know like what happened after the year AlexNet was released, 2012, to the year like 2017. But is there anything left for us to do? I was a newcomer and I didn't know much of the field at that time, but it seems that it has been like 10 years. So what was the difference? I think that was a starting point of my career path, and and also I think that was a like very fast exploration of all these kind of possibilities integrating AI with models at different scales. But to put the story short, I think the very first bottleneck was when I looked into the paper, I asked Professor Jog better for the code that is always under development, I couldn't get it. So I tried to like use MATLAB to re-implement the method, and I need to do this again and again. And I just realized that this is not the story of machine learning in the field of machine learning. So also we were quite lucky that in the year 2016, TensorFlow was just released. So built on top of TensorFlow, you could just build very freely, neural network architectures and all these kind of optimization methods. And these are something that was in many cases was maybe ignored when we introduced the scientific work. But actually, that's something most time consuming. So with this kind of opportunity realized, I think in the year 27, I think the systematic opportunity realized by discussing with my two advisors was that we could just see this thing in a very multi-scale picture, and going from quantum mechanics to all these models. I think you must have been familiar with for a long time. So there could be several opportunities. These black boxes. So going from many electron wave functions to all these bridges between different scales. So from a point of view of multi-scale modeling, so what was missing is exactly the capability of a numerical scheme that help us to address so-called curse of dimensionality problems. To model the potential energy where density functional both accurately and efficiently require accurate and efficient high-dimensional approximators which has been lacking for a long time. And that's something mathematically that we could leverage for all these kind of problems. So that was the story of methodology development at the starting point. And definitely we spent a lot of effort in this direction. I think DeepMD is one of the example, and Professor Han Wang, the next speaker, will go into details of that, so I will skip that. And what I will just also like to quickly mention is the DeepKS, DeepConsham, also machine learning based density functional, trying to make the model in some sense end to end, and also to make this a good production level solver. We also integrate this with Abacus and also make this capable of fitting not only energy and forces, but also electronic structure properties. But what was also challenging was that this would require some deeper and also some more fundamental change of electronic structure code, so which makes this quite challenging. So it's also still a code development challenge. So I will just give this one example. But what I would like to say from here is that after all this kind of quick development of methodologies, my experience was that on one hand, all these papers will always easily get rejected, and one need 1 year or two to just reply and go back and forth of all these review ideas. But on the other hand, the field has been advanced so quickly that we really need to have some users to tell us where we need to go and where this is not going to work. And so then what was interesting was that we found modern software engineering plus open source community is very important. So the incentive barrier is between code development and paper publishing. So I think every code developer could just understand what this means. And but I think thanks to the great effort, in particular Han Wang and all these developers in the deep modeling community right now, to really make this kind of solutions production level, one need cloud native workflow develop toolkits, and also this kind of neural network engines, and also like engines for MD and DFT, and a lot of them need to be in some sense refactored to better suit to be better suited for the current infrastructure like HPC and AI algorithm development. So this kind of effort is, in some sense, missing in the broad scientific community, or so typically this could be like organized by large groups, but not like in a very decentralized manner. So we're trying to do this in this way. So that's the very first set of stories. And so we're trying to make this open, and in particular for this very special timing for this world. And also, I think being open is very important. Okay, so this is the first set of story and also first set of incentive barriers. And the second one, so as the field proceed, okay, so AI gave us tools for simulating truly large-scale data. That is pre-trained models. And due to time limitation, I will not go through what is pre-trained models, but what it helps us is that we do see that AI-assisted multi-scale modeling is having some emerging bottlenecks. For large data samples, they are hardly utilized. And for hard modeling problems, they're still hard. And also, we need some better ways to be connected to experimental results. So a way is to develop pre-trained models. We could even consider developing pre-trained models from simulation data and adapt or fine-tune that from to experiments and to do more things. And that's the theme. As we have more and more data, we could consider, and we could even consider multi-scale pre-training to do pre-training at different levels and to integrate the solution to each different application. Here, I present an example of battery development. And I do see some opportunities, maybe like for along this way, but I will not go into detail for like all these deep kind of pre-trained models. And also like the broad application using one single model that it could give us. But then if we go back to the question, so what if after having this kind of opportunities, what could be the incentive barriers? So what we observed is that given more and more possibilities, or even just you have a pre-trained model, you can consider integrating that with like experimental data and also to develop like a large atomic model that Hanwang will introduce. The incentive barrier, the barrier is still like the infrastructure part of the field. So data extraction from literature and also like pre-trained model development, I think if you look at the LM industry, there's so many solutions at different sections. So which makes this thing happen. But then what if like for AI assisted pre-trained models, and actually so the open source software development is no longer enough. We still need like code development of data model and workflows and things like that. So we need a better hub to share and also continuously integrate and continuously deploy better data model and workflows. So then actually it's paper versus APPs, applications. So application-driven evaluation system and application-driven workflows and also continued development of all these kind of solutions. And that's another thing that we have been promoting recently, so-called OpenLAM project to develop like foundation models for the atomic world. Okay, so and also like to pushing all these kind of solutions not into a paper but into application apps in the platform. Okay, so this is a second thing. But very quickly, when we just consider data-driven design, actually we need to get better connected to experiments, or even we need to better integrate the whole system. So going from like literature mining and read, the designing process is typically like you design and make and test the system and then do analysis and do this iteration again. And in this loop, there are actually some essential bottlenecks happening at the bridge. And so here are some examples, like we do this closed loop. But what we do observe is that the gap happens between these bridges. So so then actually the major bottleneck and the emerging opportunity happens at the bridge between all these steps. So finding the loop of measurement, analysis, and control, and increase the scale, quality, and rate of feedback will be something needed if we integrate things in this way. But actually, right now, I do feel that like the bridge is something not so native, but actually typically physical, but not a chemically organized thing. So this is something like the third kind of question, and at this stage, how we organize things becomes the next challenge. So I do think that these kind of problems and challenges is something like one typically miss, like when we consider all this kind of methodology development. But since now the computational schemes and also all these kind of methodologies is becoming so capable, or more and more capable of addressing more and more problems, these emerging bottlenecks and emerging feedbacks systems could be something we need to consider and to improve. So for example, for the OpenLAM scheme, actually the thing we could consider is really very much depending on the data rate. So how the scale and also the feedback of data could come from. So computational data could be the first round, but then actually characterization and then manufacturing data. So these kind of things, I do think need to be integrated and considered in the whole methodology development stage in the next few years. Okay, so I think I'm close to like exceeding the time, so I will stop here. But I think overall, I think these are the three kind of emerging bottlenecks and incentive barriers for us to consider. Thank you.
Thank you very much. Thank you. Questions or comments? Please. Oh, wait, no. You need a microphone.
Okay, thank you. My name is Carmen Lee. I'm from the University of Toronto, and thank you for a nice talk. You mentioned about using pre-training model to, one of the advantage of pre-training large model is to achieve a better connection between the simulation and the experiment. And could you share some more specific thought about how to connect simulation and experiment, especially like in the experimental work, what we eventually, for example, synthesize is not exactly what is predicted from experiment. How can we make better connection using the pre-training model? Especially, I'm not sure whether when you're talking about the pre-training model, is it more about pre-training on the large computational data set, or it also include the pre-training on the experimental data set? Thank you.
Okay. So as long as we have large enough experimental data set, we could consider that. But at this moment, I don't think this is in most cases, this is practical. So actually pre-training happens for like computational or digital data. And let me just quickly give you one example, and Han could maybe introduce more. So let me introduce what I skipped, Unimo. Actually, what considered was like to start from molecular geometry that is optimized by physical models. One could have these geometries, and to do pre-training by denoising and things like that, typically unsupervised pre-training. And after pre-training, what one could consider is to do probably fitting and searching or generation like equally for many different applications like drug discovery, polymers, and also maybe optoelectronic materials design and things, all these kind of material design. And that is like pre-training from physical models, number one. And then when going upwards for like liquid electrolyte design. So in many cases, it's not only at the molecular level, but also at the mixture level. So it's actually the formulation design. So what one need is then at the next level, a pre-trained or large formulation level model. And for that, one could further do a lot of simulations from atomic models, and then one could leverage simulation results like structure redistribution functions and things like that to do pre-training for this formulation level model. And the input of the formulation level model are those embeddings from like molecular pre-trained model and the concentration. And then we have a multi-level pre-trained model. And we're developing multi-scale pre-trained model in different ways. And this is one quick example.
Okay, I think we have to move on. Thank you very much for your talk and actually also for the question. So, Li Feng, thank you.
Thank you.
We continue with the second invited talk. Han Wang was mentioned at least twice, I think, in your talk already. So it's a pleasure actually to have him here from the Institute of Applied Physics and Computational Mathematics in Beijing on simulating the microscopic world from Schrödinger equation to large atomic models. Okay.
Okay, thank you very much for the introduction, and thank you very much for the organizers for providing such a great opportunity to share our work on the large atomic model. Okay, it works. Okay. And as we all know that the molecular world is composed by atoms, which are basically a nucleus and a cloud of electrons. And the fundamental equation for this atomic world is a Schrödinger equation. Here is a stationary form of the Schrödinger equation. And if we are trying to solve it under the Born-Oppenheimer approximation, we immediately find that we have to solve such a variational problem. Here, the blue coordinates are the electron degrees of freedoms, and this is the ground state energy, and the red R is the parameter of the position of the nuclei. And this defines the potential energy surface of our molecular system. And even for a very simple molecule like the water molecule, such an equation is very high dimensional. The blue degrees of freedoms are of 30 dimension, and the red coordinates is of 9 dimension. Here immediately comes the curse of dimensionality. And from the mathematical perspective, we were lacking powerful tools for consider such of high dimensional problems. And this is already pointed by Dirac in the 100 years ago. And in the past 100 years, as a computational community, people are developing very powerful tools for practically solve this Schrödinger equation, for example, the density functional theory. And it reformulates the many electron Schrödinger equation by the Cohen-Sham equation, which reduce the dimensionality of the problem from very high to only 3. Therefore, we can solve it very efficiently for practical systems. But the cost we have to pay for such dimension reduction is that, firstly, we introduce the non-linearity into the problem here. And then the second is that we introduce an unknown term in the Hamiltonian, which is called exchange correlation. And in Professor Xu's talk, we have heard of a very great volume of effort to model either by traditional way or by machine learning way the exchange correlation functional. And the second challenge faced by the DFT that the computational complexity of such a method is still very high. And this plot gives you the Cohen-Sham DFT calculation on the world's fastest supercomputers. And we see that from 2006 to 2019, the peak performance of such computers grows by almost 3 orders of magnitudes. But the system size handled by such supercomputers is grown by only 1 order of magnitude, which align almost perfectly with the cubic law of the growth. Therefore, DFT calculations are still very expensive nowadays, and the typical system we are doing with is of order of hundred of
atoms. And this stimulates a very fast development of the machine learning potential energy models. The starting point is the DFT calculates the data, and we provide a bunch of positions of nucleus and compute the ground state energy, and many of these pairs from our training data. And by training, we mean that we try to minimize the difference between the the deep learning model, the prediction of the deep learning model with the DFT calculated ground state energy with respect to the model parameter, which is denoted by omega here. And why do we use deep learning models? From mathematical perspective, is that deep learning or deep neural networks are very powerful tools to representing high-dimensional functions. And here are works from the mathematical perspective explaining why the deep neural networks are good tools for high-dimensional functionals. And we also say that the founding fathers of the deep neural networks are awarded by the Nobel Prize this year. Okay, if the training is successful, the deep learning models are hopefully they have a comparable accuracy as DFT, and at the same time, the computational complexity is reduced from the cubic order to the linear order, which means that we can handle much larger or much larger system with a much faster speed. And this is achieved actually on the supercomputers 2020, and we see that the system size is extended by almost 4 orders of magnitude, and at the same time, the speed is also increased by 3 orders of magnitudes. And this can be this is achieved by on a GPU installed supercomputer, and this can be further boosted by hardware especially designed to machine learning models. For example, this kind of FPGA chip or ASIC chip. You can see that the ASIC chip almost boosts compared to GPU machine learning molecular dynamic simulation. It boosts the efficiency by 3 orders of magnitude, or saves our power by 3 orders of magnitude, which means that we can do much faster and much environment-friendly machine learning molecular dynamic simulations on such hardwares. Okay, the machine learning potential energy models are very powerful tools, but the problem is that these machine learning models have to be built one model for one specific system. This may not be a big challenge if we only want to study one specific molecular system, but if we switch to the problem of materials design, we have to consider a large chemical space to play around, and we don't want that for each new element we have to do a new model, and this situation would become much worse if we consider multi-component materials, and the possible number of systems will grow exponentially large. And one way to solve the problem is, of course, to train a universal model for such a large chemical space. But if we go one step further, we consider that the types of atoms form the material is enumerable in this periodic table, and all the atoms, no matter what type of or what chemical species of the atoms are, they are governed by a universal Schrödinger equation. And from this universal Schrödinger equation, then it's possible to train a universal machine learning model to solve all the potential applications in the materials world. And this is the idea of developing universal or fundamental models for the potential energy surface. And to work along this direction is listed in this table, and one representative example may be the genome model published last June materials on the convex Hall. But the problem is that the main challenge faced by such model is that they can train only with the materials with the data from the materials community, and the problem is why we cannot use, for example, the training data from the chemical community. That basically these training data are labeled by different functionals. And in the chemical community, they are searching for very expensive but accurate functionals. But in the materials community, people are basically satisfied with PBE. All this data cannot be combined together so that the scalability of the data cannot be increased very across the multi-field of the research. And obviously, this kind of data from different fields can actually share some common knowledge. For example, the catalyst data is composed by materials with open surface with a small atom on the open surface. It's actually they share knowledge with the materials data and the chemistry data. And the challenge is that these large models developed currently cannot use all of the data fields of research. And to solve this challenge, we have proposed the large atomic model and the DPA2 as a possible prototype for this model. The whole workflow is composed by 3 parts: the pre-training part, fine-tuning part, and distillation part. And first, the pre-training part, the key idea of using data from multiple fields is that this is a traditional single task training, and we lump the unified structure of the model together and to train the data from multiple fields all together, and to update the descriptor from by the gradient from all the data from the different fields. And we also want that the common knowledge is deposited into this unified structure, but the field-specific data is deposited in the fitting net. It's a specific structure for each data set. Therefore, the capacity of the model in this fitting net should be much smaller than the unified structure. Therefore, we have proposed our DPA2 descriptor for the unified. It's very powerful or very deep model structure, and it is connected to the currently very popular graph neural net model in the sense that it can be viewed as a kind of a graphic neural network model, but the difference is that we have we have more node updating mechanisms, and we also evolve the edge features by self-attention mechanism. This is the difference. And we want to point out that the multitask training scheme here is actually much important than the model structure innovation. We will explain. Okay. The first is that the training accuracy. If the question is that if we can train simultaneously on all the data sets from different research fields, the answer is yes. And we compare our multitask training with the traditional single task training. We see that we almost have very little lost in the accuracies. The second is that once we have trained the model on this multidisciplinary data, and how do we justify the transferability or generalizability of the model? We have tested the zero-shot generalization error. That means the model is not trained by the downstream task, and whenever it's pre-trained, it's directly used to predict in the downstream problems. And we see that the multitask trained DPA2 achieves better performance. And we also use the same model structure DPA2 to train on a single materials data set. We can see that it has a comparable accuracy with all the large models trained by the same data sets. That means that model structure is actually not very crucial to the model performance, but the multitask training and the data set from different research fields is a crucial part to enable the good generalizability of the model. And I want to skip this interesting example. And next, whenever the unified descriptor or common structure is trained, and the knowledge is transferred to a downstream training problem, and we train the model in the downstream scenario, and we investigate the data efficiency by these plots. The horizontal axis is the size of the data set, and the vertical axis is the error. We consider energy and force errors. Please notice that all the axes are log scaled. And the blue curve is a model from scratch, and a green curve is a model, pre-trained model. We can see that a great improvement is achieved in all the downstream problems. And the representative example is that we can achieve the same accuracy with 100 times data reduction, or use the same amount of data. We have reduced the error by 1 order of magnitude. And the third step is the distillation. The idea is that the downstream model is very expensive because it uses a very heavy structure, the unified descriptor from the pre-training stage. So this model is very expensive. But if we want to apply it to a very specific problem, the model capacity may not be such large. And we want to pursue very high efficiency. We also want to pursue very high efficiency in such downstream tasks. Therefore, we let the heavy model as a teacher model and use it to label structures. And it is used to train a very lightweighted and highly efficient student model for this specific downstream task. And we see that the speed and the system size are increased by 2 orders of magnitude by such distillation procedure. And the speed can be further boosted by use machine learning AMD processing unit, the hardware, to further accelerate the efficiency. And we consider the accuracy in the typical applications, for example, the ferroelectric materials or the solid state electrolyte. And all the cases, the distilled model are of satisfactory accuracy. Okay, as a summary, and we are still at the very early age of the large atomic models, and the crucial part to boost the generalizability of this large pre-trained model is to use the multitask training scheme to incorporate as much as possible data. And the further development importance of course is the data set and also the benchmark workflows, which has already mentioned in the Linfeng's talk. And we also have started the open source large atomic model project. You can freely download all the training data and the model from this website. Okay, I want to acknowledge all the collaborators and the funding support, and thank you for your attention.
Okay. Thank you very much. Do we have questions or comments on this talk? Yes, one. Okay.
Hello, I'm Nikita Rybin from Skoltech. I have a question about train and test errors, actually. So when you use these unified models, would the test and train errors allow you to actually construct an accurate convex hulls? So let's say if I'd like to screen the whole chemical space of some simple molecular crystal or some alloy, would this train errors of like 50 milliev per atom allow to construct the convex hull?
Yeah, you mean, okay. Of course, as the data set grows, the capacity of the model should be increased so that the accuracy of the multitask trained model can be comparable by the single task model. And in our test, we find that the current model capacity we are using, whenever it's trained on all of the data set, it can reach almost the same accuracy as the model trained on a specific data set. Therefore, that means that the current capacity of the model is enough for all the data sets. And you are correct that when the size of the data set increases or we incorporate more fields of the data, we may have to increase the capacity of the model. Sure.
Okay,
Thanks.
Rampi, one more question before lunch.
Yeah. I'll make it very quick. Thank you. So I'll make it very quick. So when you sequentially train on newer training sets, does the performance on the older set degrade?
You mean the knowledge forgets?
Yes, exactly. Does it remember or does it forget?
Yeah, in the downstream task, whenever you incorporate new data from the new task, and you can also use the multitask training scheme that you have one head specific for the new task and the other head simultaneously trained on the old data set. Therefore, it guarantees that the old pre-trained data, the knowledge from the old pre-trained data set is not forgotten in the downstream task by this kind of multitask training scheme. It is possible. And we have tested, but not showed by the slides, that whenever we use this multitask training in the downstream task, we have a much higher generalizability as the single task downstream training or downstream fine-tuning. Thank you.
Okay, thank you very much to our speaker. And I think actually I'd like to thank everyone who was speaking and asking questions. And now we are going for lunch, and I think Yi has to tell us how.
Okay, so we'll have a lunch at Lehu Hotel, the first floor. If you know where they are, you're recommended to just walk there. But for most people who are not familiar, please take a bus. It's very short walking distance, but it's better to take a bus without a lot of walking. Okay. 我们在乐乎那个新楼1楼吃午餐啊，如果是上大老师知道怎么走就直接走，不知道的话在门口做报